Let's get started. Welcome to the final class for CS188. We have made it here. We have, as always, a couple of housekeeping things to get through before we begin. The final project is due tomorrow. So yeah, one note so if you have extensions, it's possible that you have extensions at this point. Like the last day for extensions on the homework, I believe, is Wednesday of next week. And then the last day for extensions on the projects is Friday. So make sure that if you have extensions that you get everything into us by then, because that's the last day that we're going to grade stuff. There will be a review session. We might get through the topics that we're hoping to cover today a little quick, and so we'll try and do some review at the end if we have time. But there will still be a review session. We're just trying to get a room for that. So see details on Ed. There will be a post once we've locked that down. And finally, course evaluations. Currently, our response rate is at a whopping 20%. That's up a lot from last week, so good job. But it's not quite at the 100% that we're looking for. So we've added this incentive for you all. There will be 1 percentage point extra credit on the final exam, and that unlocks once everybody gets to at least 70% response rate. So you have to get your responses in by May 5th if you want to unlock this extra credit. But once 70% of you respond to the course evaluations, everyone gets access to this plus 1%. So if not doing it for yourself, do it for your friends. Okay. So without further ado, let's talk about artificial intelligence one last time. We've covered a lot in this class, but before we get into sort of our last lecture for the day, I just want to draw your attention to this picture that we have here. And I'd like everyone to just acknowledge and thank our amazing artist who drew all the pictures back in 2012. So Katrina Yim drew all the pictures for the class, and the fact that we have slides that look as beautiful as we do is really thanks to that artwork. So yeah, so just want to acknowledge that. And here's sort of the big tableau of all the little guys that we've experienced and encountered so far. We've covered a lot of ground, right? We covered search, we covered games, we covered logic, we covered Bayes nets, we covered MDPs, we covered Markov chains and HMMs, we did machine learning, reinforcement learning. We learned what evaluation functions are. We learned about heuristics, sampling, all this stuff. So yeah, that's a pretty wide range of topics to cover in one course. And remember at the beginning I said, okay, if you want to get a job in AI, this is probably not the class for you because, we're going to focus on sort of classical techniques. Why did we do that? Why wouldn't we focus on sort of the state-of-the-art, most cutting-edge stuff? So you might be thinking I learned all this cool AI stuff, but how is this going to be useful to me out in the world? And I would claim that it's going to be useful to you, and I'm going to try and prove that it's useful to you in this lecture. So I guess one of the reasons that we want to cover all of this sort of broad foundation AI stuff is that it makes it really easy, hopefully, we'll see in this class, if you have that broad foundation to learn a new thing. So when, it seems like every day there's a new algorithm or a new model coming out or a new sort of data pipeline, and having the sort of broad foundation that we've covered in this class, all of these things should hopefully make it easier to understand new concepts when they come up. So here's a new concept that has come up recently, right? This is today's AI, right? So here on the left we have ChatGPT-4. On the right we have Claude 3 Opus. These are sort of two of the top large language models that are out there today. And how do they work, right? This is sort of, when you think of AI today, this is kind of what people are thinking about. So can we take all the stuff that we used in this class, all the things that we've learned, and can we kind of try to get a sense of what's going on inside of these large language models? Well, let's see. So large language models, I will claim, use a bunch of the things that we have already covered in this class, and with a small number of upgrades, we can actually get all the way to large language models. Okay, so what's in a large language model? Well, at the beginning, we're going to have to do some feature engineering because we have to, we have some model. We want to take the world and put the world into our model and out comes something useful. So we have to do some feature engineering. These language models take text as their inputs, and they have text as their outputs. So we're going to need to come up with some mapping from text to sort of like neural network land. So we'll get into that, but we'll cover text tokenization and word embeddings. Then we'll get into sort of the details of what are these networks, what's the shape of them, what are the different components that go into them, and we'll build things up hierarchically. You'll see that of the networks that we've looked at so far, these are probably some of the deepest ones, so deep neural networks. And they're composed of components that are then composed of components that are composed of components. But those final layer of components are composed of things we've already seen before. So we can go up like 3 levels, and we should be able to get there. Then at the end, we're going to be predicting a word. And there's a finite vocabulary. So this is really just a multi-class classification problem. It's saying, what's the next word? And if you have a finite vocabulary, you have a finite set of classes, you're really just doing classification. So the objective is your sort of classic multi-class classification objective that we've seen a bunch of times. We'll train it with a version of supervised learning. So we know what supervised learning is. This is when we have some human labeler or some sort of right answer that's associated with each of our data points. And we're going to get into this idea of, well, what happens if it's too expensive for the human to label all of the data? Is there a way that we can come up with a scheme for building ourselves a labeled data set without having to go in and label everything by hand? And so that's this idea of self-supervised learning. And then instruction tuning is sort of like, how do you make the most of your limited amount of, or your expensive human labeling capacity? So when you do have a human, how can you use them effectively? Then we'll do some more reinforcement learning. We love reinforcement learning. Now we'll do reinforcement learning from human feedback, and we will try to align these systems with what we think humans want, and we'll hopefully get more useful models out. And finally, we will show that, like, in order to implement that, it's going to be difficult with the types of networks that we're going to be seeing, but that the policy search, which we introduced sort of at the end of the reinforcement learning unit, that will get us sort of most of the way there. And then you add sort of gradient descent and policy search together, you get this idea of policy gradient methods. So we'll cover that briefly. And there's one more thing that's kind of just for fun, but like it actually does make these models work better, and it's the return of beam search. So remember beam search from like when we were doing the optimization and the hill climbing stuff? So beam search turns out to be a useful thing that you can use with large language models as well. Okay, so all the stuff in blue we've seen already, and hopefully with a small number of these sort of sub-bullet point upgrades, we can get ourselves to understanding large language models. That's the roadmap. All right, so here's a deep neural network, and it does its neural networky thing, and what we want is for the input to be text. We want the output to be text, some more text, and that might look like this, right? I have some sentence, that's my input. It's a partial sentence, the dog chased the, and I want my network to output some guess as to what the next word is going to be. Maybe it says ball. Okay, the dog chased the ball. So text is like discrete, and this neural network is implemented with like linear algebra, and those two things don't know how to talk to each other. So how are we going to connect this discrete text-based vocabulary, this finite set of possible things that someone can say, and connect that to the linear algebra and tensor arithmetic that our neural networks take in? Well, we're going to do that in a couple of stages. The first stage is we're going to break up the text into pieces. This is called text tokenization. So we have some long sequence of characters here. We've got words and emojis, and we've got some numbers in there, right? And what text tokenization does is it says, all right, let's break that up into pieces that we're likely to see. Okay, likely to see many, many times. So a text tokenizer says, I have a couple of characters. Here's an A, and here's a B, and I can treat those characters as either independent, or I can combine them when I see two characters next to each other, and really frequently we can sort of like merge them together and build like a single token. So this tokenizer will divide up our words into chunks. And these little chunks are sort of this is going to amount to what our vocabulary is. So rather than characters or words, it's some sort of hybrid between characters and words. And so you see that sometimes, entire words like many map to a token. But other times you have indivisible, which ironically was divided in order to make 2 tokens. So the tokenizer will decide sort of, how best to separate the words or combine the characters together in order to make it so that we have this vocabulary that's manageable. Okay, so we've now divided all these pieces up. We have all of our tokens. Each of these tokens is then going to be associated with a number. So the first piece is breaking stuff up into chunks, and the second piece is taking each chunk and assigning it an integer. Okay, so we're almost there, but neural networks don't take integers either, do they? They take sort of vectors. They take real numbers as their inputs. So how do we get from these integers to sort of like neural network land? Well, here's the big picture, right? So we take our sentence, we have the dog chased the, and then we're going to tokenize that, and maybe we'll just say for the purposes of this slide that each one of those gets its own token. Turns out that they actually do with this particular tokenizer. These are the numbers. I ran it through the OpenAI tokenizer, and these are the numbers that came out. So those are the tokens for these words. Okay, but these are just integers, and what we want are sort of vectors. So we're going to embed these integers using, essentially, we're going to assign each one of them a vector, and now each one of them has a vector. Okay, so 791 maps to this dark blue vector, and then 5679 maps to the light blue vector. Now we have vectors. Our neural network can use those vectors to predict another vector. No problem. We've seen this before. And then we can try to unembed that vector using the reverse process. We take the vector and we try and figure out which of the tokens is it most likely associated with. Maybe we get 5041, and then we would untokenize that and get the sort of text output. So one thing to note here is that this is typically what's called a one-hot representation. Who's seen one-hot representations before? Okay, many people have. I'll just say for the folks that haven't seen them, what they look like is they look like this. We have a vector, which is just a list of numbers, and a one-hot vector is a vector of all zeros, right? Except there's going to be like one spot in the middle where we have a 1. That's the hot vector. It's the one hot vector. And so for the first example, we have 791. That's saying that the 791st entry in this vector, if we're assuming like 1 indexing, would be a 1, and the rest would be zeros. So what this is saying is now we have a way of going from this integer into a vector of real numbers. It's 1.0, 0.0, and then we can go from that vector of real numbers to a sort of like an embedding vector, which is just some arbitrary vector pointing in some direction. Okay, so this uses one-hot vectors. So these are the embeddings, but I just said that these are like random vectors. Like, what do these vectors actually look like? Let's try and get a sense of what these vectors are. So it turns out that words cluster by similarity. Who can read the words? I can't read them that well from here. They're like kind of faint. Okay, so I'll point to them with the thing. So we have, oops. All right, so over here we have train, bus, car, college, school, work. So like there's kind of like a cluster in this section. These are like, I don't know, transportation vehicles. And then we have sort of here, this is like places that you can learn, and then this is like places that you can work maybe. Over here is like prepositions. These are sort of like activities or like exercises. This is sort of related. It's like going. It's like just travel. And then down here we have sort of another couple of prepositions. I'm not sure why those are down there. And then we have sort of like articles and like pronouns and stuff. So you can see that these are sort of like clustering by similarity in this vector space. So we're drawing it in 2 dimensions. Really, these vectors are many dimensional. And so they might actually look more like this. If we have a vector of real numbers and we sort of like, if we make sure that they map to, if we normalize them so they're between 0 and 1, what we might see is, we have a lot of different numbers side by side. We can put two of these words next to each other and see what their embedding vectors look like. So the first two we have here are sea and ocean, which are, not necessarily the exact same concept, but they're very similar concepts. Like there's a sea, there's an ocean, you can swim in them, you can, can drive a boat on them, you can do whatever. There's like marine wildlife in them. A sea and an ocean are roughly similar, and you see that like these two representations are quite similar, at least if you compare either one of them to sort of football, right? Football is much more distinct from sea and from ocean than sea or ocean is from each other. So we're seeing that like these features that end up getting learned by these language models kind of make some sense. They sort of tell us what's similar and what's not. And that's what's allowing us to do this kind of clustering, and this embedding space is sort of like a meaningful space. All right. If you're still not convinced that there's like kind of semantics, like meaning encoded in these vectors, here's another picture. This is actually from 2013. So it turns out that you actually get like a kind of a sensible algebra in the embedding space. So if you take the vector for man, okay, so this is the word man, and it might look like this. And then you take the vector for the word king, which might look like this, okay, and you subtract one from the other, you get sort of the difference between king and man. And that's sort of like royalty, I guess, right? So royalty is sort of like this axis between king and man. And this is like, if we call this the royalty axis, then what we could consider is like if we added this royalty to the word woman, would we get sort of the corresponding word? And it turns out that we do. Like you can add this royalty vector to the woman vector and you end up with the word queen. So this kind of works in a couple of interesting situations. Here's just one example. But like, if you were worried that this isn't capturing meaning, based on this illustration, hopefully this should sort of convince you that there is some aspect of meaning being encoded in these word embeddings. Okay? Questions so far? Yes. Is this related to perceptrons because we have a vector and you shift it around? I think it kind of is. Yeah, I think, in the sense that like the perceptron, we had these features and we wanted them to be sort of representative of some concept. And then we would classify if we were close to that concept. Yeah, you could imagine doing sort of like a dot product between two of these vectors, and you can say like, let's go back to this example. Let's take a dot product between sea and ocean. We're going to get I always have to remember, is my dot product going to be small? Yeah, the vectors are going to be very close together, so we'll have a small dot product. But if the vectors are sort of like in completely different directions, like football and ocean, then we'll get like a big dot product, right? Because there's a big angle between them. So yeah, you can kind of think about these as sort of like what we talked about in those lectures. Yeah, more questions so far? Feature learning, embeddings, word embeddings, tokenizing. Okay. So just a quick shout out to this interactive sort of website visualization. This is where this came from, and I can't remember if this also came from there. So this interactive is pretty good, and if you're curious for sort of like more visualizations, you can go check that out. We're using it a little bit in this class. Okay, so that's the feature engineering. Let's keep going. Let's do the deep neural networks stuff, right? So we've seen neural networks before. What extra pieces do we need on top of neural networks to make all this work? Well, the first is autoregressive models. So we have this network, and if we feed stuff into it, something comes out. But when we interact with these chatbots, we don't want them to predict one word. We want them to predict many words. So how do we get them to predict many words? Well, this is where autoregressive models come in. So the idea with an autoregressive model is you have to start somewhere. You just put a word in, and you put a bunch of padding tokens, and then you feed that word into the network along with these padding tokens. You predict the next word, and it maybe predicts, maybe it predicts dog, right? Then you take the word dog, you make a second sort of copy of the same network, and you feed the dog into the next network. This is really the same network as before, you're just using it a second time. And then you keep padding, and now you predict again. So it's called autoregressive because you're using sort of past outputs as sort of like future inputs. So this is saying like on the first pass, we're going to input one token. On the second pass, we're going to use the first token and the output of the first pass as our second token to get a third token, right? And so now we have the dog, and we predict chased. And then we take, we instantiate the network again, and we're going to feed in more inputs. We say the dog, chased, and another padding symbol. And then we say, it predicts the, and then we take the, and we feed it over here. And then we say, okay, now we have a sentence with 4 words in it. We'd like to predict a 5th word, and maybe it predicts ball, right? The dog chased the ball. Right? So this is like using the network to produce the inputs that we don't have yet. So if imagine you're a chatbot and someone, asks you a question, you can predict the first word, no problem. You've trained for this. This is what you've been waiting for, is to predict a word. You predict one word, and then the way that the system works is it takes that word and it concatenates it on the end of the initial prompt. So we have the original prompt, and we have the first word of the response, and then we feed that back into the network, and the network predicts another word. Everyone see what's going on here? Autoregressive models. Okay, cool. So the idea is we'll predict the output one piece at a time. These could be words, they could be tokens, they could be pixels if you were doing sort of vision stuff. But an autoregressive model is predicting one piece at a time. We concatenate our input with whatever the output is that's generated by our model, and then we feed the result back in as our new input, and we run it again. That's the concept with autoregressive models. So just to visualize that, we have some x. This is like the first input. We're predicting x2 from x1. Then we're predicting x3 from x1 and x2. Then we're predicting x4 from x1 through 3, etc. Right? This process just keeps going. Okay, so when we get to n, we're really conditioning on lots and lots and lots of variables. So this is saying, like, if I have a long paragraph, and I'm a large language model, and someone inputs this, like maybe they input a whole document. If I want to predict, or maybe they've asked me to produce a document, or they've asked me to produce like a long section of code. When I'm predicting the last token of this long sequence, I have to condition on all of the information that came before that. And this might be quite a lot. Some of these models have context windows that are like millions of tokens at this point. So this could be a lot of information to condition on, and it's not clear like if we need to be paying attention to all of that information. Okay, so this is where the idea of self-attention mechanisms comes in. Self-attention mechanisms say that instead of conditioning on all of the input tokens equally, if we're trying to predict this x6 here, instead of looking at all of x1 through x5 when we're trying to predict x6, what if we pay more attention to relevant tokens? Right? So this is also going to help us to generalize, because if x1 and x4 are not relevant, then they could be anything. And so any sentence that has any x1 and any x4, as long as we're paying attention to the other sort of relevant information, we can now generalize. We can make good predictions, and we can sort of generalize across combinations of words that we haven't seen before, because we're sort of filtering out the words that are not important for making this prediction. This is like a type of abstraction. It's saying, throw away some of the information that's not important so that we can generalize over the information that is important. Okay, so this is the concept of self-attention mechanisms. How does that work in sequences of text? Well, imagine we have this sentence. The dog chewed the bone because it was hungry. if we were looking at the word it, that's why I've circled it or highlighted it in yellow here, or orange. What is it referring to? Take a look at this. Is it referring to dog or bone? Yeah, dog, right? It was hungry. The dog was hungry. That's why the dog chewed the bone. Okay? So we can take these attention maps. This is like saying, where are we attending to? What are we paying attention to in this sentence? And we can sort of like show that there's connections between some of these words and the word it, and not from other words. So like it's much stronger connection from dog to it, and it chewed it, and it was hungry, right? Than there is to bone or because or was. Okay? So that's the basic idea. But imagine a different sentence. We have the dog chewed the bone because it was hungry. What if we had the dog chewed the bone because it was delicious? Now what is it referring to? Now it's referring to bone, right? And so our attention map would say that bone is much more relevant when we're looking at it, and delicious is now relevant. So we would have a different attention map. It's saying that what it means in this context is different from what it meant in the other context. So this is sort of like what attention mechanisms are doing for us. They're saying, in certain contexts, words behave certain ways, and we should try to identify those contexts. So we should be like on the lookout for contexts that tell me it is playing the role of dog, and contexts that tell me that it is playing the role of bone. And I should treat those contexts differently when I'm trying to predict the next word. Because, if I'm in a situation that's more like a bone situation, then I should predict delicious, versus if I'm in a situation where I'm in more of a dog context, then I should predict hungry. Does everyone see that? So this is attention mechanisms are just sort of telling us about the context around which we're trying to predict the next word. Yeah? It will learn how to make connections, based on sort of like adjusting the weights of the attention mechanism. And we'll get into sort of what the attention mechanism looks like in a sec, yeah. Other questions? Yeah.
I have a question about the autoregressive model.
Okay, autoregressive model, yeah.
Is it somewhat similar to like RNN?
Is it similar to RNNs? It is similar to RNNs. So RNNs, I can't remember if we covered those in this class. So it was in the project, right? So with RNNs, right, we have this recurrence setup, right? So we take the network, and then in order to train it, we have to sort of unroll it, and you have like you feed in one sort of input, and then you feed in another input, and then you feed in another input, and you're using the same weights at every time step, but you need to sort of like back propagate through time in order to train the RNN. So here that would be like the words in a sentence. And you would say, okay, I'm going to start with the first couple of words. My RNN might predict a new word as an output, and then I'm going to feed all of those words, including the new word, back into my RNN and go again. So yes, RNNs are sort of like the original way that you would do this, and we've sort of with the architecture for large language models, we no longer use recurrence, but we still use this sort of autoregressive approach. There are ones that don't use the autoregressive approach, but I think most of the big ones now do use that. Yeah. Other questions so far? Yes?
So with the autoregressive model, how does it predict each next word or next token or next thing?
How does it predict? Yeah, so I haven't told you necessarily how it predicts, but you can think of it as a classification problem where you have, let's say you have n words in your vocabulary, or n tokens maybe. You just want to predict what's the probability that the next token is this particular word or this particular token, right? So what's the probability that, I have the dog chased and the next token is ball, or the next token is car, or the next token is person, right? Or the next token is other dog, right? I don't know. Other dog it might be more than one token, but right, so you're predicting what's the probability of each of these being the next thing in the sequence. And you would also be predicting for all the other words in your vocabulary. So the dog chased the, sky. right? That's another word in your vocabulary, but it's not likely, right? So your model would hopefully have a lower probability when it's predicting what the next word is for sky than it would for ball. Okay? But it's classic sort of multi-class classification. But we haven't quite got to that point yet. So like, let's figure out how are we going to build these networks, right? So we have this self-attention mechanism. It's this cool idea where we're going to be paying attention to the different contexts, and that's going to help us generalize. How do we implement self-attention? How do we implement this thing? So we take some input. Let's call that x1. This is like the first token in our sequence. This could be the word the in our classic sentence. We're going to feed that into a couple of these multi-layer perceptrons. So you've all seen these things by now. It's just, a couple of perceptrons stapled together. The output of this is 3 different sort of vectors. We're going to call these key, query, and value for reasons that kind of don't matter. So we have a key, a query, and a value. We're going to take the dot product of the key and the query, and this gives us a score. Okay, so this is a process by which we can say, like, how much should I be paying attention to x1? This score is saying, like, how relevant is x1 in this context? This is like the score that is ultimately going to determine how much attention do you pay to this particular input x1. How important is the in my sentence? Okay, and we're going to have one of these for each of the inputs, and that's actually going to be sharing the same weights. So we're going to have another one of these key, query, value combinations on top of x2, and we'll feed in x2 and we get another score, and we feed in x3 and we get another score. And each one of these, we're going to be looking at these scores, and we're going to see which one of these scores is the highest, which which scores are large scores and which scores are small scores. So what we're going to do next is we're going to normalize these scores, and we're going to do a softmax operation. And this is like this is basically just saying, let's make all of these numbers sum to 1, and we can basically attend to the numbers that are larger. So this is going to give us our attention weight, and then we're going to say, okay, I'm going to attend to x1 with weight a1. I'm going to attend to x2 with weight a2, and attend to x3 with weight a3. Okay? So I'll let you stare at that for 1 second before we kind of do the last piece. But this is how we're saying, okay, I have a bunch of things in my context. I have x1, x2, x3. How much attention should I be paying to x1 and x2 and x3? Well, it's this much attention, a1, a2, and a3. So we're going to let the network figure out what are the weights that go into these multi-layer perceptrons in order to get the right attention weights out. It's going to figure out all that stuff for us. We don't have to think about this. Okay? So then the last piece is we multiply this value that we generated by the attention score. So this is like we take our input x, we run it through a multi-layer perceptron to figure out some features that are sort of like internal model features. Who knows what neural networks do with this stuff? And then we have this v1, and we're saying, all right, well, there's a v1, there's a v2, there's a v3. We should be attending to the v1 that came from x1 with weight a1, and then we should multiply those two things together. And let me just make some room up here. We're going to add all of these things together at the end, and that's going to be sort of the thing that this predicts. There's like a couple of nuances that I've sort of I've skipped for the sake of time here, but this is roughly the picture. So you have an x1, it comes in, you figure out how much attention should you pay to that, and then you incorporate the value v1 into your final output accordingly with this attention weight. So what is this x prime? This is like the next x in the sequence. So if the sequence is just x1, then you're predicting x2. And you're ignoring sort of all the future context stuff. All those attention weights will end up being 0 because you've added padding symbols, and maybe the network learns that when there's padding symbols, you don't care. So you can sort of downweight the attention for the future stuff, or you might even mask them out entirely and say, just 0 contribution from all that stuff. Then when you get x2, you feed x1 and x2 into your network. Now you're predicting x3. And once you have x3, you can feed in x1, x2, x3 and predict x4. And each time the network is looking at all of the different inputs, it's encoding them to this sort of these values and these keys and these queries, and it's figuring out how much attention should it be paying to all of the inputs. And so that's how it's coming up with these different weights, the ones that we saw a little while back. So like, how does it compute these weights? It computes these weights using this process. Okay? So all the pieces here are things that we've seen before. It's like it's perceptrons and dot products and just normalization and sums and things like that. And all we're doing is we're using them in a new way, and this is what's allowing us to achieve this kind of attention style behavior. Okay. So the language models today love this idea. They say attention is so good. This is like, what if we had more attention? Okay, so what if we had multi-headed attention? So we started with sort of single-headed attention, and now we want to think about what would multi-headed attention look like. This was like the picture that I just showed you. It's now simplified so that we can fit everything on the slide. So we feed in x's, and then we do this self-attention thing, and out comes our predicted next word. Well, we can do this in parallel. We can have multiple attention mechanisms, and each one of these will have different weights associated with it, and maybe these things can attend to different things. And then at the output, we'll get these sort of like internal vectors that we would then concatenate together and have the network figure out how to combine them. That's like this last concatenate plus MLP thing. And then the output would be just one step further removed. It's saying like, first we do single-headed attention in parallel a bunch of times, and we get sort of like individual predictions according to each of these different attention mechanisms. And then we combine the results somehow. We let the network figure out how to do that. Okay, so why do we want multiple heads? Why do we care about multi-headed attention? Well, because it lets us do stuff like this, all right? So here's one of the heads that this network might develop over time, right? So our sentence here is, the girl and the boy walked home. Okay, and this particular attention head, I'm visualizing on the left in gray. Sorry, my microphone keeps falling off my ear. Okay, on the left in gray is the word that we're predicting, and on the right is the word that we are sort of conditioning on. Or the words that we're conditioning on. But what you see is that this particular attention head is always looking at the previous word. Okay, so this might be an attention head that focuses on the previous word in the sequence. So maybe we want a head for that, right? Maybe usually like the last word that someone said is going to be somewhat predictive of the next word that they're going to say. So this is a useful thing to pay attention to. Is that the only thing that we want to pay attention to, though, when we're predicting? No, of course not, right? So we might need another attention head that does useful things for us, like pronoun references. Imagine we have this sort of two-sentence phrase here, right? The girl and the boy walked home. She took his hand in hers. Aw. Okay, so we look at the word she, and we say, what is she attending to? Oh, you kind of can't see it. That's kind of frustrating. All right, so I'll sort of fill it in here, because there is an actual relationship here. So it's kind of interesting. There's a connection here that is like a little faint. It's hard to see. Okay, so we're attending to girl. We're attending to, well, this one kind of doesn't matter. And then when we get down to his, can you see it? Yeah, you actually can't see it. That's kind of a shame. So when you look at the slides later, you'll realize that you can believe me. But this one is actually attending to boy, which is nice. Like his hand, right? Whose hand? The boy's hand, right? And when we get to hers, it's attending to, hopefully you can see it this time. Yeah, hers is attending to she. So you can at least believe me on the third one. So this thing is figuring out, when we say she, are we talking about the boy or the girl? Well, we're talking about the girl. When we say his, are we talking about the boy or the girl? We're talking about the boy. And we talk about hers, we get sort of she, and she refers back to the girl. So this is kind of doing pronoun references for us. And so if we're trying to predict, the next word in the sentence, having these pronoun references as an additional thing that we're paying attention to might be really useful. And so we might have lots and lots of these attention heads. and each one of them could attend to different things. So we might do previous word, and we might do pronoun references, and we might do like parts of speech and like connections between subject and object, and we might do like, yeah, sort of like if there's like a count that if we're counting numbers like 1, 2, 3, like we might pay attention to the last couple of things in the count and seeing like how much we're counting by. Yeah, there's like all kinds of patterns that the network can pick up on if we give it multiple attention heads. So that's why we're using multiple attention heads here. Okay, does this make sense? Sorry that the slides couldn't come through on the screen here. But if you look in the PDF, you'll see that this is actually true. Okay, questions on multi-headed attention? All right, nice. Oh yeah, question. Yeah, so I had the same question. Why is there a connection between she and stuff in the future, right? Like SEP. And what is this SEP token? I believe SEP is like a separator token. It's saying like there's a separation between sentences. And then CLS, I think that's something to do with like the start of a clause maybe. Or yeah, it could be the start of the sentences. I'm not sure exactly. But yeah, why is this attention mechanism attending to stuff in the future? And I think what that's saying is like, so there's different ways that you can train these models. Sometimes you'll have them predict the next word, and sometimes you'll predict missing words in a larger context. So you have a whole sentence, and you just like take one of the words out from the middle, and then you try and predict that word given the rest of the sentence. And so this attention mechanism, I suspect, was trained in that way. So it's just attending to stuff in the future. Sometimes what you'll do is you'll say, okay, let's mask out the attention from stuff that happened in the future, because I can't condition on stuff I haven't seen yet. If I'm doing this autoregressive thing, you might need to do this masking so that you have like only the stuff that came already is conditioning your next token. Yeah, thanks for the question. Does that make sense? Cool. Yeah, other questions? Okay, so now we're going to use multi-headed attention inside of another neural network block, and we're going to talk about the transformer architecture. So yeah, I've tried to like repurpose some of the cartoons from earlier. Like they didn't talk about transformers back in 2012 because they didn't exist yet. So we're in completely uncharted territory now. But all right, transformers, like what are these things? This is like the thing that's inside of all of the like new language models. Technically, there's like a couple of new architectures people are working on that don't use transformers. But like the major ones all use transformers. So what's the transformer architecture? Well, it's like a transformer block, and then we're going to stack a bunch of transformer blocks on top of each other. Each of the blocks uses pieces that we've now already seen, right? There's this normalization layer, there's a multi-headed attention layer, then there's another normalization layer, and then there's another multi-layer perceptron. There's just like 4 of these blocks inside of a transformer block. And then we might have n of these transformer blocks stacked in a row. So we're going to keep transforming and transforming and transforming. Okay? Very simple concept. This turns out to be really, really powerful. So you stack a bunch of these things together, and you just put your tokenizer on the front end along with your word embedding. And then on the back end, you have this unembedding step and this untokenizing step. And then you just have n transformer blocks in the middle. So that, remember, these transformer blocks are just normalization, multi-headed attention, more normalization, and a perceptron, multi-layer perceptron. So we stack n of those. Usually n equals 6, although I don't know if that's true for the sort of latest and greatest models, because some of these things have lots and lots of parameters. But in the original like transformer paper, I think this was 6. And so you put in your sentence, the dog chased the, you tokenize it, you embed it, you send it through a bunch of these transformers, it figures out what to attend to, and it says, okay, well, the dog chased the. So if I'm going to predict the next token, I might be paying attention to the previous word, the. So I'm looking for a thing that the could be attached to, the something. It should be like an object or some sort of phrase that starts an object, right? Like it could be, the dog chased the shiny, right? Shiny could be a reasonable next word, but shiny would then have to, there's still like an object that we need to sort of fill in here. So we're kind of in that object mode when we're sort of predicting the next word. So our attention heads can be telling us these kinds of things. And then there's one more note here, which is that when we get to this unembedding step, this is really just a multi-class classification problem. This is multi-class classifier. So what that means is we have some embedding. This is like a vector. This is saying here's the vector that we predict as sort of our next next embedding. But that embedding might not be identical to any of the vectors in our vocabulary, right? We have a vector for each of these tokens. They point in all these different directions. Some of them are different colors from before, right? And we want to predict what is the most likely next token. Well, we have some vector. It's pointing in some direction, but that might not be any vector in our vocabulary, right? So what we do is we say, all right, it's close to some of the vectors that we saw. And so we do the classic multi-class classification thing. And there was a question earlier that's like, oh, is this kind of similar to like the perceptron stuff? And yeah, it is. Like at this point, we have some vector that we've predicted. Maybe we have another vector that's like one of the vectors in our vocabulary. And then we can compute like a dot product between these things. Maybe we normalize the results so that we have probabilities over our possible vocabulary. And those should hopefully sum to 1. And that allows us to predict with some probability what's the likelihood of this word next, what's the likelihood of that word next. And so now we have like predictions over what the next word is going to be. And these things sum to 1 and everybody's happy. Right? So that would give us this would give us sort of a prediction vector with like probabilities in it. So we might say like 0.9, it's ball, right? 0.05, it's, I don't know, shiny. And 0.05, that's like all the other stuff, right? So the rest of our vector adds up to 0.05. Probably it's not going to be this certain of anything, but so now we have this prediction vector. These are all the probabilities, and we can just sample from this, right? So we have a vector of probabilities. We know how to sample from a vector of probabilities. So we sample from it. We get an output, and that output is a token. It's a number. Maybe it's 5416. I can't remember if that was the number for ball. But if it is, then we output ball, and that will be the next text in the sequence. Okay? So we've stacked all of these transformers. Each transformer has a multi-headed attention inside of it. Each multi-headed attention has a single-headed attention inside of it. And the single-headed attention is sort of doing the work of seeing what's important. Okay? Layers on layers on layers. This is why they're called deep neural networks. All right. So that's the whole left side. That's great. We've crossed all this stuff off our list. And we've already talked about a few more of these things, right? So supervised learning. Well, now we have these large models. It's going to take a lot of data to train all these parameters. We don't want to have a human go in and label all of these examples. Ideally, we would like to be able to construct large data sets so that we can train these really hungry models without someone going in and labeling everything by hand. So do we always need human supervision to learn these features? Can we learn general purpose features without human labels? Well, maybe if we have like a really clever label generation procedure, maybe we don't have to have a human go in and label everything by hand. So the key hypothesis here for what people call either unsupervised learning or self-supervised learning is if we have a neural network that's smart enough to predict, for example, the next word in a sentence or the next frame in a video or generate realistic images, if it's smart enough to predict those kinds of things, then that same neural network is ready to do supervised learning from a very small data set. So if we can sort of like get ourselves off the ground without human labels, then maybe we don't need as many human labels, and maybe that'll be cheaper to build a data set. So what does this look like? We have to do task 1 and then task 2. First, we have to train a neural network that is smart enough to predict those kinds of things, predict the next word in the sentence. And then we have to use that same neural network with our sort of like small data set of carefully crafted human labels, and maybe we can get it to do something useful for us. Okay, so this is like transfer. So task 1 is we do an unsupervised learning task, or we do a self-supervised learning task. And task 2 is like the real task. That's what we want this thing to do. In a language setting, we have some text that's the input. Maybe our first task is just predict the next word. Task 2 could be like sentiment analysis. Is this like a positive review or a negative review? Like if it's a movie review, is it positive or negative? So first we train a model that can predict next words, and then we try to predict the sentiment. We do sentiment analysis on like movie reviews. But models that are good at predicting next words might be better at predicting sentiment than models that can't predict next words. This works for images too. You can take a chunk out of an image. The one on the left is like someone has removed a chunk from this image, and then the one on the right is actually like a reconstructed version. So there's like kind of a blurry patch in the middle here. I don't know if my, for some reason my laser pointer's not working. But there's this section in the middle. It's sort of like fuzzy here. I don't know if you can see that. But it's like predicting the middle part. So this image model is now pre-training by predicting the missing patches in these images and trying to make sure that it looks like seamless, which this one's pretty good. It's a little blurry. Okay, so that's pre-training, and then there's fine-tuning. So, okay, the first step, task 1, pre-train a large language model or a large model, could be a vision model, on lots of data with a self-supervised task. This could be predicting the next word, etc. Predicting the next word or the patch of the image. Could be predicting a missing word or a patch of an image that's missing. If two images are related, we could try and predict that, or unrelated, like maybe this is an image that we've shifted from a previous image, or maybe this is an image that's like completely different. Like distinguish between these two totally unrelated images, or tell me that this image is just a rotation of the other image. So this is what's called contrastive learning. There's lots and lots of like self-supervised or unsupervised tasks that we can give to our models. Once we do all of that, hopefully our model is like decently competent at whatever our pre-training task was. Step 2, fine-tune. Continue training that same model to do the thing that you really care about. Okay, so in the case of text, this is called instruction tuning. So task 1 is we build this model that's going to just learn to mimic human written text. It reads the entire internet, and then it tries to predict the next word in a sequence for lots and lots of sequences. So if we ask it, what's the population of Berkeley, it might complete that human input with, this question always fascinated me. Right? What's the population of Berkeley? This question always fascinated me. That's not a super useful response. Sometimes you'll say like, what is, what event happened in 1066? Please write, and then the completion will be like, please write a three-paragraph essay on the importance of this event. And it's like. That's not a useful that's not a useful completion. So maybe it's human-like because that's something that you can predict. But what we want is helpful text. So task 2 is how do we get this thing to generate helpful text? Not just text that looks like text that it saw, but helpful text. And this is where instruction tuning comes in. So instead we'll give it a query, and then we'll have a human go in and give a helpful completion, right? They'll look up the answer, they'll say it is 117,000 people as of the 2021 census. That's a much more useful answer if you ask about the population of Berkeley. You can fine-tune on collected examples of these helpful human conversations, and now the model will start to produce outputs that are answering questions instead of just extending questions. We can also use reinforcement learning. So that's kind of like another approach. So usually we'll do some pre-training, we'll predict the next word, then we'll do some instruction tuning. This is called supervised fine-tuning. And then once the model is kind of like answering questions, we can do this other piece, which is called reinforcement learning from human feedback. So reinforcement learning, we have to have an MDP, right? We're always doing MDP stuff. I mean, I guess we could do like a partially observable thing, but like in this case, we only need a Markov decision process. So reinforcement learning from human feedback, let's define an MDP for this problem. Well, the state is just going to be the sequence of words that we've seen so far. So what is the population of Berkeley? And this is really big, right? So this is like, if we assume that the sequences can be 1,000 words long, like 1,000 words or 1,000 tokens, then if our vocabulary is 100,000 words or tokens, then it's 100,000 raised to the 1,000 possible states in this MDP. That's a lot of states. It's huge. But maybe if we do some clever like feature vector stuff like we talked about already and we use neural networks, maybe we'll be okay. Like we just have to define the MDP for now. Okay, the actions are going to be, what's the next word, right? These are the things that the model can do. The model can predict words. So the next word might be it might be chair, it might be purple. There's lots and lots of words, maybe 100,000 of them that it could predict. If we're doing like Q-learning and we have, remember I said, when we switch from value function learning to Q-learning, we multiply the size of the value function by the number of actions. Well, if the number of actions is 100,000, this is going to be really big. And if the size of the state space is 100,000 to the 1,000, we can't write down this value function. We just can't. Okay, so it's hard to compute the max over actions when there's 100,000 actions, most of which you probably haven't tried before, and you've never been to certain states before. You haven't seen these sentences before. So this is going to be challenging. But the transition function is easy, right? We just append the action word to the state words, right? So if the sequence, the input sequence, the state is my name, and the action is, the next state we know it. It's my name is. Super easy. Okay? The reward, this one's an interesting one. So there's a few things we can do for the reward, but basically what these models do is we have humans rate the model completions. So we have a human prompt, it goes into the model, or maybe we have like an automatically selected prompt, but in any case, we put the prompt into the model, and then we say generate two different completions. Here's completion A, right? My name is, and here's completion B, my name purple, okay? So the human would then rate those two completions and say which one do they like better. Thumbs up for the first one or thumbs up for the second one? Do we prefer A or do we prefer B, right? So what's the population of Berkeley? It is 117,000. Maybe we give that one a thumbs up. And it is 5. Maybe we give that one a thumbs down. Or maybe the sort of like the B answer was destroy all humans, right? And maybe we thumbs down that one as well. So we're comparing like hopefully a good response and a bad response, and hopefully our feedback will be enough that we can learn this reward function. Okay, so +1 for good responses, -1 for bad responses. So we learn a reward model. This is like an estimated reward model. And we use that for model-based RL, right? So we don't have to compute value functions. We think value functions are going to be complicated. But hey, the transition function is really easy. As long as we can learn this reward function, maybe we can do model-based RL. Okay? But we still need to come up with, like, what is this network going to do? And we need to somehow represent this policy. And the way that we're going to do that is we're going to do policy search. So the last thing that we talked about in reinforcement learning was policy search. This says I'm going to explicitly represent my policy instead of like taking a max over Q values or something. I'm just going to have a policy. And I'm going to change that policy so that over time it will get more and more rewards. Okay, so that was supervised learning and RLHF. But now let's talk about policy search. Right, so we're rummaging through these possible policies. We're trying to find a good one. The way that these large language models typically work is they use what's called policy gradient, which kind of staples together the ideas of policy search and gradient methods, like gradient descent. So we initialize this policy somehow. This policy is going to be a stochastic policy. So it's going to be the probability of choosing each action conditioned on some state. So whereas before we had like a policy was a deterministic mapping from states to actions, now we're going to let this policy vary. It's going to be, selecting actions probabilistically. And what that allows us to do is we can change the parameters of that probability distribution gradually rather than in discrete jumps. And that makes the gradients work out a lot nicer. We get a much smoother optimization landscape. So we need a performance a performance objective. Like this is how good is our policy. So we call that J. J of a particular set of policy parameters. The policy is parameterized by this vector theta. These are, you can think of this as like the probabilities associated with your probability table. So if this table maps from S's to A's, then there's a theta for every SA combination. So J, the performance metric for a given theta, says let's figure out what the value function is under that policy for the starting state. Or this could be an expectation over a distribution of starting states. Let's just leave it at this. So what's the value of the starting state? Okay, and then we improve the policy by, we could do hill climbing. We could change theta, evaluate the new policy, keep it if it's better, and keep doing that repeatedly. But policy gradient says we're going to actually do gradient ascent, right? If we can estimate the gradient with respect to the policy parameters of this objective function, then we can change theta to ascend this gradient. And so all we would have to do is take a step, move from theta k to theta k plus 1 in the direction of steepest ascent of the objective function. So whatever direction I can move my policy in order to maximize this objective, that's going to say that I'm going to get as much value as possible from my starting state. So all we have to do, and I'll put that in sort of like scare quotes, is because like there's some nuance to it, is like we have to estimate this gradient of this objective function, this gradient of J. Once we do that, we can just repeat. So initialize the policy somehow. It's going to be a stochastic policy. We estimate the policy performance. We try to improve the policy. Here we're going to use gradient ascent, and then we repeat. Okay, so how do we estimate this policy gradient? We won't have time to go through the theorem in this class, so I'll just sort of show it to you and then tell you intuitively what it means. But we're going to need to define something called an advantage function. This is using the same value functions that we've seen already. So Q functions and V functions. Q functions say for a state action pair, if I'm in some state and I take a certain action and I commit to it, no takebacks, how much value could I get if I take that action from that state and then act according to my policy thereafter? And then V says, all right, you don't have an action choice. You just have to act according to your policy from state S. So what this advantage function A is saying is, how much more value could I get if I took action A in state S than if I followed my policy in state S? How much better is it to take action A than whatever I would normally do with my policy? That's the advantage of an action in a given state. And one thing that we can note is that the expected TD error, remember the TD error is saying how surprised are we when we're estimating a value function. I see an R plus a gamma times a next state value and I say, oh, that's better than I thought. I was only expecting V of S, but I actually saw R plus gamma V of S prime, and that was bigger. So I have a positive TD error, that's good for me. I should increase my value of state S. So whenever I'm surprised, that's my TD error. The expected TD error turns out to equal the expected advantage. So this is nice because now we have a way of estimating this advantage. We can just estimate the TD error. So if we want to estimate this A, we can just already compute the TD error. We know how to do that from previous lectures. So we take samples of A by taking the TD error. And then there's this nice theorem that says, and I won't prove it to you, but it says if we let tau denote a trajectory, this is like a sequence of state actions and rewards for like an arbitrary episode. The gradient of this objective thing as a function of the policy parameters is equal to an expectation of a sum of the advantage functions at every state action pair times the gradient, this is kind of a mess, of the log probabilities of the policy. So let me sort of take you through the pieces. This is saying like, this advantage function is saying, when A, some action A, is better than my policy, this gradient here is saying, increase the probability of that action. When this A is negative, it's saying decrease the probability of that action. So when we have like when we have a lot of benefit of taking this action over following our existing policy, the advantage is going to be positive and it's going to be large. And we should make a big change to our policy to incentivize taking that action as opposed to our policy actions. On the contrary, if A is really negative, then we should definitely downweight that action in the future because it's way worse than our policy in general. Okay? So that's the concept here. And it turns out that we can train that, we can estimate that the same way that we do with sampling in sort of other parts of this class, right? So in the reinforcement learning unit, we talked about how do we estimate expectations using sampling. You do a similar thing here. You gather a batch of n trajectories, n episodes. For each one of those episodes, you're going to sum sort of like all the things that you saw along that episode. This part here is just the TD error. This is this delta thing, r plus the difference here, right? And then this part is saying how much should we change the policy by when the TD error says good things happened. So the TD error says, I was surprised. I was expecting this to not be that good when I was in state S. But actually it was pretty good. I saw r plus gamma v of s prime, and it was way better than I expected. Well, whatever action you took, take that action again. Take that action more, right? So that's what's going on here. It's saying we should always look to see how surprised we were by what happened. And if we were surprised and it was a good surprise, take that action more. If we were surprised and it was a bad surprise, take that action less. So we won't have time to prove this policy gradient theorem, but hopefully you can kind of get an intuitive sense of like what it's doing. It's saying when we take an action and it turns out great for us, better than we expected under our policy, we should take that action more. And when it turns out bad for us, we should take that action less. Okay, so that is the policy search and policy gradient piece. And there's one last piece, which I think is kind of nice to just tie everything together, and that's beam search. So remember beam search? We were doing hill climbing, and we said, all right, we can do hill climbing. And so we start with some state, and it has some sort of value associated with it. And we can do the successor generation thing, and we can come up with sort of like next states. Imagine we're starting with words, and now we're predicting like next words. And so like our beam search sort of like continues, and we have these values associated with like the various sentences. And we said with beam search, we said, okay, first we said we could rerun hill climbing multiple times. We do like random restarts. We try it and we might get a better value. We can restart as many times as we want. And the random restarts, the execution will go like this. First we do one pass, then we do another random restart, then we do another random restart. That felt inefficient. So we said, all right, well, why don't we do parallel search? We do all of our random restarts in parallel, right? Computation just goes like this, much more efficient. And then with beam search, we said, well, what if these searches could talk to each other? You know, we start with these states. They have these objective function values. We generate successors from those states. And then we take the best performing ones and we propagate those into the next round. And then gradually over time, we keep the best ones each time and sort of rank them. And beam search is like focusing on the most promising candidates in our search. So that's beam search. We can use beam search, and so it sort of like extends in this direction. So we're focusing most of our compute on the places where we think we have the highest objective value. We can use beam search in the language generation case as well. So we have about, more, a, and base. These are like all the possible completions of this sentence. So this is like, this graphic was made by the Financial Times. They say the Financial Times is about, the Financial Times is more, the Financial Times is It's kind of hard to evaluate these things. So if you just rank these things, I think this is a video, right? Yeah, let me run the video. Yeah, so if you just rank these things, you get sort of the probabilities that you would predict each of these tokens next, right? About is probably the most important one, and then more. And so you have like the rankings of these different choices. Let's say we went with about, that's what we sample. The next word would then be economics or some other set of values, and so we pick economics, and then we have and podcasts, right? The Financial Times is about economics and podcasts. Okay, so I guess this is an advertisement for the Financial Times. But if we do this in parallel, we might get multiple different sentences, and these sentences don't really look that much like each other. we can estimate the reward for all of these different sentences. We can look at our sort of RLHF reward model, and we can evaluate the whole sentences with beam search. And then we can keep the ones around that are the most promising. And so what might happen is we end up selecting, once we generate the whole sentence, we might decide that actually this sentence is better. So rather than doing a greedy search and we get about economics and podcasts, we realize that if we do beam search, the Financial Times is a newspaper founded in 1888. Maybe that's a more useful completion. So beam search is like another thing that we can add to the picture here that makes these language models perform really well. And now we've crossed everything off of our list. We went back and we looked at all these concepts that we looked at throughout this class, and now we kind of have a sense of what these language models are. Okay, so this is like super exciting. It says, all that stuff that we learned, it means that we can go off and we can learn about new stuff, and it won't take us quite so long because we have this solid foundation of all these different concepts. Okay, so where could you go from here? Well, language models build this kind of like structured concept space, right? So we have the words upward and airplane over there. We have river, water, ocean over here. Can we use other data? Can other data be put into this space, like images? Like if we have an airplane image, can we put that next to the airplane? If we have a heat map of this person's foot, I don't know if this is like how they're running or something, or a stop sign, can we put those into this space? Can we build sort of like image and audio models, or image and audio and text models? Can we build a single model of all these data types? If this picture of an airplane was invented by Wright brothers, who invented this picture of an iPhone, right? So could a model answer that question? Right? Well, look at this graph and tell me which was the fastest growing news source according to, I don't know, is it the Financial Times? I guess it's it's probably the internet. Okay, so great. And then if this pattern of pixels changes into that pattern of pixels, what does this pattern change into? Like, can we get sort of like common sense reasoning out of this thing? Maybe if we build a model of all these different data types, we can get there. People are working on this. I won't go into the details of this slide, but this is like a slide from Google. But tracking progress, like how well can AI do on human tasks? Well, here's a bunch of tasks. This is like AP calculus tests and code forces rating and a couple of other ones like the bar exam, the GRE, the LSAT for getting into law school. Okay, there's a bunch of tests. Turns out, like as you go over that direction, turns out that the AI models can do quite well. So blue is GPT 3.5, light green is GPT 4, and then dark green is GPT 4 if you add vision. So if you build one of these kind of like hybrid models that's vision and text. So we're starting to be able to solve a lot of these classic human benchmarks. And so that's kind of interesting. We have to figure out if the benchmarks are good enough or what that means for humans. But forecasting progress, basically, so people have developed what are called scaling laws that say you can extrapolate the performance improvements that we've seen in the past. And if we make the model bigger and if we add more data, the trends seem to continue. What would the accuracy become? Well, it just kind of keeps going down, right? Like, so if we make the model use more compute, our loss keeps going down. If we make the model bigger, it keeps going down even more. And if we train with more data, loss keeps going down. So like, we don't know how long these scaling laws will go for. They're not really laws per se, but they're like scaling trends. But it's interesting that so far we haven't seen any sign that these trends will stop soon. So that's kind of exciting and kind of maybe nerve-wracking depending on if you attended the last lecture. Yeah, some capabilities can emerge unexpectedly once these models become really big, right? So after a certain size, 13 billion parameters in these language models, and suddenly you get a big jump. And then 175 billion, you see a lot of other models like now have a big jump in performance. So we should be paying attention to these kinds of things and making sure that when models do things unexpectedly, they do what we want. Okay? So what will AI's impact be in the future? Well, I guess that's kind of up to you now, because you have all the tools that you need. If you go off and you do research, or you go off and you become an engineer, or you could be an auditor or a regulator, you could be just someone who's informed about AI now. But you can go off and do whatever you want with this stuff. You can try and figure out, which classes do you want to take next. There's a long list of classes. Here's the code for this class. But here are lots of classes that you could take next. Some in machine learning, some in data science, data ethics, probability, optimization, cognitive modeling, machine learning theory, computer vision, deep RL, natural language processing. And then there's a bunch of like special topics classes that have like those CS194 dash somethings. There's probably more that are not here. Ask the TA staff or ask us if you're interested. But yeah, lots of places to go next. One place you should all go next is help us with the course evaluations. And then look on Ed to see details for the review session. Thanks so much for being here. It's been a pleasure. And we can use the last, 4 minutes to answer questions if anyone has questions. All right, thank you. And thanks to Michael also, and to the rest of the TA staff who really are part of the reason that this class was successful, because we definitely couldn't have done it without them. It was our first time teaching, so we learned a lot about this process. So thanks to all of you for bearing with us while we figured out the kinks. And yeah, thanks to the TA staff as well.